Okay, good afternoon, everyone. My name is Christina. I'm also a professor here, part of CSAIL, and I work on computer architecture and computer systems. So what I want to do today is tell you a little bit about the work that we've been doing recently on improving how efficiently cloud resources are being used, given the slowdown of Moore's law. So first of all, let's see what are the challenges with respect to cloud computing that we're thinking about here. Cloud computing has existed for about the past 15 years, and in this time it has gone from hosting a small number of large applications to practically every application from every domain of human activity. So these are applications from which we have come to expect high performance access at any point in time and from any place in the world. So clearly it is important to keep improving the performance and efficiency of the backend systems, the data centers that host these applications. And that being said, there are a couple of recent trends in cloud systems that make that more challenging. One is on the hardware side, and the other is on the software side. So let's look at the hardware first. This is my obligatory end of Moore's law picture as a computer architect. So for a long time, computer architects had a relatively easy time in the sense that any time we needed better performance from the hardware, we could rely on the device technology to shrink the transistors without increasing the power dissipation of the device, and that way give us better performance, higher frequency for the same cost. And that's no longer the case. The NAR scaling has ended, which gave us the constant power density, and Moore's law is slowing down, and that has pushed a lot of computer architects to look for more specialized solutions, whether these are through special purpose chips or reconfigurable accelerators. So there's a lot of good reasons why people are switching to specialized architectures, and I should also say that that's nothing new. Specialized architectures have been around for many decades. What is new is that these accelerators are increasingly finding their ways in cloud infrastructures, and that did not used to be the case. The way cloud systems got a lot of their cost efficiency benefits is by using economies of scale, by using commodity equipment and then buying hundreds of thousands of copies of that, and that way being able to drive down the cost. So again, there's a lot of good reasons why people are switching to these heterogeneous accelerators, but it also means that we have to manage a much more complex system than what we previously did. And then on the software side, we have a similar story of increased complexity because of the way that cloud applications are designed today. So traditionally, applications were designed in a way that looks something like this, so a monolithic design. And I'll talk about each of these two application frameworks in more detail over the next few slides. Over the past few years, a lot of production environments have moved to much more fine-grained, event-driven application frameworks through the microservices and serverless programming frameworks. And again, there's a lot of good reasons why that transition has happened. We'll see it over the next few slides. But it also means that we have a much more complex application graph, application topology that we have to manage. So we have this story of increased complexity on the hardware side and also increased complexity on the software side. And that's exactly the reason why we have to rethink how to architect cloud systems, both from the perspective of using existing resources more efficiently, given that Moore's law is slowing down, and also from the perspective of abstracting away as much of this complexity as possible, both from the end user and in many cases from the data center operator as well, the cloud operator. So this is an approach that can be applied across the system stack. For the purpose of this talk, I'll focus mostly at the hardware level. So how do we design platforms that use resources more efficiently? But again, it's an approach that can be applied across the system stack, from hardware design to how to manage resources, whether that is at the granularity of a single machine or the granularity of the entire data center, how to debug issues with those resources, how to design programming frameworks that then users can leverage to write their applications, and all the way to what are the right languages, what are the right compilation techniques that make it easier to write these very complex application topologies, whether they're entirely running in the cloud or whether there is some application component that's running on edge devices. Okay. So for the rest of this talk, what I want to do is focus on this transition from monolithic application design to microservices as a use case for why we need to focus on using existing cloud resources as efficiently as possible. So we'll see in a bit more detail what monoliths are, what microservices are, what are the advantages and disadvantages of each programming framework. And then we'll see what data center tax operations are, so why they are required, why they consume a large fraction of the CPU cycles in cloud environments today, and why that becomes even worse when we have these new programming frameworks like microservices. And I'll tell you about two ways that we can go about reducing this data center tax overhead. One centers around proposing new hardware that accelerates computation related to data center tax, and the other has to do with software optimization, and both are valid approaches. They just have different trade-offs. Okay. So a little bit of background on what the different programming frameworks are, and probably many of you are already familiar with monoliths and microservices, but just to make sure everybody's on the same page. So what I have on the slide is kind of a cartoon version of what a monolithic application looks like. So let's assume it's a social network. So on the left side we have the web server, and that is what the users will interact with. They'll send requests, which will first hit the web server. And then on the right side, we have the backend databases, which is where all the state is being maintained. And that can be in memory, or it can be in persistent storage. Usually, it's a combination of both. Everything else that implements the logic of the application, that is where the monolithic design comes into play. So everything else is going to be a single code base, and it will compile down to a single binary, which then gets deployed on a machine. If at any point in time this application needs more resources, the only thing I can do is scale out multiple copies of that binary across multiple machines. And I should preface the discussion between monoliths and microservices by saying that the monolithic application design is perfectly fine as a first step. It's perfectly fine as long as your application is low in complexity and small in scale. Where this breaks is when the application becomes very large in scale and very high in complexity. And the reason why it breaks is because it makes it very difficult to continuously develop and continuously redeploy the application without making significant changes to your existing code. It also makes it quite difficult to adopt new frameworks. You're kind of limited to whatever language or programming framework the whole application is written in. And it doesn't help this idea of an elastic cloud, an elastic data center, which means that anytime I need more resources, I can just scale out to more resources. Because even if a small part of this application, let's say just the posts operation here, even just a small part needs more resources, the only thing I can do is scale out the whole thing. And that would waste resources, which is not what we want to do, given the slowdown of Moore's law. So these are some of the reasons, the primary being the difficulty of quickly developing the application, why a lot of production services have moved from the picture on the left to the picture on the right. So the front-end web server and the back-end databases, those have remained the same. What has changed is the part in the middle. Instead of having one large application that implements everything, we now have this graph, this topology of smaller, simpler applications where each focuses on a very small fraction of the overall functionality. And then they talk to each other over the network. So they transmit data over the network. There are several advantages to this approach. The primary one is that this is a much more fine-grained way of building applications, which makes each component easier to understand. If I'm in a group where I only want to make changes to the ads application, I just need to know the code for the ads application and what is the API to communicate to the rest of the topology. I don't have to know the details about every component in this complex topology. The second advantage of this approach is it's more elastic. If, again, the ads application needs more resources, I can scale out the ads application. The rest of the topology can remain as is. And it gives you some flexibility with respect to the languages or the programming frameworks that you can use. Let's say for the front-end services, a higher level language makes more sense, as opposed to the back-end services, which are more performance sensitive, and you might want to use a lower level language. You have that flexibility. We can discuss to what extent you want to have a lot of different languages in the same topology, and probably you don't, because it adds complexity, but at least you have that flexibility. Now, that doesn't mean that microservices and any of these fine-grained event-driven application frameworks do not come with their own set of challenges. Specifically, I've replaced a single application with this complex graph that might have hundreds, if not thousands, of unique applications. And each of these unique applications now has its own resource requirements, and I need a system that is able to understand them and manage them. Also, these applications talk with each other over the network. So there is a lot more pressure for low latency, high bandwidth network connections. And even though if you go and read the design principles of microservices, you'll read that they say they should be loosely coupled. So there should not be a lot of traffic, a lot of communication between them. In reality, they're not entirely independent from each other. And because systems are not perfect pipelines, there's queues in between components. These services have dependencies, and these dependencies can create performance issues which propagate and amplify across the system. And these issues are very difficult to diagnose and very difficult to recover from. So this is more of a cartoon version of what these applications look like. This is a slightly more realistic version. So this is a social network. It's an application that we built a few years back when we wanted to study what are the implications that microservices have across the system stack. So you can think of it as a quite simplified version of Twitter, where you have users that follow other users, and there is this broadcast style distribution of a user's posts to their followers. So the way this works is we have the client, and they will interact with the front-end services. If we have many web servers, there's going to be a load balancer in advance. Then we have all the logic tiers, and that is what implements all the functionality of these components, where a user can add posts and add images and videos and follow users and get recommendations and advertisements and all of that. And then finally, we have the backend databases. And the backend databases are going to be in memory or in persistent storage or a combination of the two. And now, depending on what request a user might send, a different fraction of this topology would be involved. Let's say they're doing something simple. They're signing up for an account, or they're logging into their account. This only involves a couple of services. If they're doing something more complex, where they're adding images and videos and links and tags to other users, and then they're distributing that post to all their followers, a larger fraction of the topology would have to be involved. So this is one example out of a set of applications that we built a few years back, and the goal of this, again, was to study what are the implications that microservices have across the system stack. And these are applications that each have tens of unique microservices, and they come from different domains where this application framework is being used. So what changes? What are the implications of microservices? There are many, but for the purpose of this talk, I'm narrowing it down to 3 main points. The first is that, perhaps counterintuitively at first glance, microservices tend to be much more sensitive to performance and predictability compared to traditional monolithic applications. So that might be a bit surprising because they're much simpler. So technically, they should be able to tolerate more jitter in performance. But in reality, if I have replaced a single application with a chain of hundreds of smaller applications, my performance, my latency requirements for each of those components are going to be much stricter. So even a small amount of noise is going to have a big impact on the end-to-end performance. Second, there's a lot more time that microservices spend in the networking stack and the operating system stack. Why? Because they communicate with each other to transfer data from one to the other. And finally, there's dependencies between tiers, which, like I said before, can cause performance issues which propagate and amplify across the system, and these are very difficult to diagnose and to recover from. Now, even if we take a step back before we switch from monoliths to microservices, if we look at how CPU cycles are used in cloud environments today, there's a very large fraction of CPU cycles that does not go towards application computation. So this is what is referred to as data center tasks. And what data center tasks means is operations, tasks that are required for the cloud to operate correctly, to function correctly, but are not part of the application logic. So this can be things like networking, garbage collection, memory allocation, scheduling, tracing, memory move, serialization, anything like that. What I have in the bottom of the slide are 2 studies. The one on the left is from Google from a few years back. Actually hasn't changed that much. And the one on the right is from Meta from just a couple of years ago. And at least the one from Google, what it shows is out of all the CPU cycles in the entire fleet of Google servers, what fraction goes towards useful computation as opposed to all these other data center task operations. And you see that, for example, memory allocation accounts for almost 10% of the total CPU cycles at Google. Memory compression, again, is over 5%. Serialization, close to 5%. Networking, close to 5%. So all this, when we're talking about millions of servers, amounts to a huge amount of compute requirements and compute resources that do not go towards useful computation. And then the figure on the right shows the same thing, a bit more aggregated from Facebook's data centers. So blue is application logic, and then the yellow is everything else, all these data center task operations. So this was not for microservices. This was for monolithic applications. Let's see how this changes for microservices. Because microservices have a lot less compute per tier, per component, data center tasks becomes even more significant. So if we look at just one example of data center tasks, just networking, what we see in this figure, so this is for the social network application that I showed you in the beginning, each of the bars is one microservice in the topology, and then the last bar is the end-to-end performance. And these 6 microservices are characteristic of the rest of the topology. So the green is the application logic, yellow is the time spent for RPC processing, and red is the time spent at the transport layer. of networking. So this is something that if we go now from low load to high load, it becomes much worse because there's a lot of queuing happening in the networking stack. And if we go from median or average latency to tail latency, it becomes even worse, again, because a lot of queuing happens in the networking stack. And keep in mind that these applications, the performance they care about is tail latency, is not average performance. Why? Because they want most users, most end users to observe good performance. So not only do microservices not make data center attacks better, they actually make it worse. So that was one example when it comes to networking. There's a lot of other data center tax operations. What this figure shows, again, this is from the Facebook experiments, shows the same analysis for memory-intensive operations like memory copy, memory move, garbage collection, and memory allocation. So at the top, it shows data center applications, and in the bottom, it shows the more traditional CPU benchmarks that a lot of computer architects use for our experiments. And the main thing to point out here is that there's a huge difference. So if what you're using is the benchmarks in the bottom, you're going to get a very different idea about where CPU cycles are going compared to if you're using representative applications like the ones in the top. So how can we improve that? How can we make sure that CPU cycles and memory are used more efficiently in cloud systems? There's two main approaches. The one is keeping the amount of resources, the amount of compute resources required the same, but accelerating their execution. And that typically requires proposing some new hardware or repurposing some existing hardware for this purpose. So the advantages of this approach is that it will free up CPU resources that then can be used for the application logic, which is what general purpose CPUs do better. They can offer significant performance improvements, in many cases efficiency, power efficiency improvements as well. And because they don't require any changes to either the application or a lot of these kernel level functions, they are transparent to the user. The disadvantage is it requires new hardware or it requires repurposing some existing hardware for this scope. So that's the one approach. The other approach is reducing, not introducing new hardware, but reducing the amount of CPU cycles that are required for these data center tax operations by doing some software optimizations. And the advantage of this is no new hardware. The disadvantage is it requires an in-depth understanding of where the CPU cycles go, so potentially new instrumentation and a lot of data analysis, and it might require some application changes. So the purpose of this talk is not to say that one of the two is better. Both are valid optimization approaches. They have different trade-offs. So let me show you an example of the first. The specific data center tax that we're trying to optimize here is networking, because we did the motivation experiment before, and we showed that microservices tend to spend a large fraction of their time processing network requests. In addition to that, microservices have very specific and very different characteristics when it comes to their network requests compared to traditional cloud applications. The first is that their requests tend to be very, very small, which means that traditional interfaces like PCIe, if we want to offload network processing to hardware, are not going to be very efficient because they're not designed for small requests. They're designed for large data transfers, especially streaming. Second, different microservices have very different sizes for their RPC request and also require different configuration parameters from the networking stack. That means that this is not the kind of computation that we can offload to a hard-coded special purpose accelerator. There needs to be some reconfiguration aspect to it. And finally, RPC processing consumes a lot of CPU resources currently, like we saw before. And in addition to that, there's a lot of interference between threads that do the network processing and threads that do the application logic processing. And that can result in very significant increases in tail latency. So given these network characteristics, we built Dagger, which is a reconfigurable acceleration fabric for network processing, specifically for microservices, but it also benefits traditional cloud applications. And it relies on three main design principles. The first is offloading the entire networking stack, including the RPC layer, to hardware. So your typical networking stack would look something like this. You have the physical layer, which runs on the NIC. You have the network and transport protocol layer, which run at kernel level on the CPU. And then you have the RPC layer and the application, which run at user level, again, on the CPU. And instead, what we do here is push everything from the application down to this hardware-accelerated network interface card. Second, like I said, this is a reconfigurable fabric, and the reason why it's a reconfigurable fabric is because there's a lot of variability, not only on the sizes of requests across applications, but also on the configuration of the networking stack. What I mean by this is that some applications might need a specific load balancer. Other applications might need non-blocking, asynchronous, as opposed to synchronous RPC. Other applications might need compression or encryption or a mix of both. So it's not the case where we can have just a single hard-coded implementation of the networking stack. So this requires programmable hardware, and specifically we do this through an FPGA. And finally, we have to offload the networking stack to a closely coupled accelerator. The reason why this needs to be closely coupled is because we want to avoid as much of the data transfer overheads as possible from the CPU to the accelerator and from the accelerator back to the CPU. And the way we do this is by using a cache-coherent NUMA interconnect, which essentially sees the FPGA as another NUMA node, and we can rely on the hardware coherence protocol for all the data transfers. So let me show you how this works. If I can skip this. So what the server platform looks like, so this was a couple of years ago, so this is a Xeon E5 platform. We've also evaluated it with newer machines, and the FPGA is an ARIA 10GX. The specific FPGA doesn't matter that much. What I want to highlight in this slide is how much of the area of the FPGA it takes to accelerate the entire networking stack, including RPCs. And this is not a particularly large FPGA. The reason why I'm highlighting this is because it doesn't take that much, and the fact that it doesn't take that much has two benefits. First, we can use the rest of the FPGA for other data center tax operations in addition to networking. And second, the fact that we're offloading networking to this accelerator does not mean we have to give up the benefits of multi-tenancy, which is one of the main advantages of running applications on the CPU. You have a lot of CPUs, and you can map a lot of applications on the same machine. You can do the same thing here and instantiate a separate network interface card for each of the different applications. You can also apply techniques for security and performance isolation between them. So a quick comparison on how this works in terms of latency. This is tail latency and throughput. We're comparing it to two types of systems. The first are software systems, so systems that do optimizations either at kernel or user level in the networking stack, and also hardware systems. So some of these are reconfigurable and some are special purpose chips. And the high-level takeaway from here is that both with respect to latency and with respect to throughput, there are significant improvements. When it comes to the comparison to software systems, it's obvious why, because we have this specialized hardware, which is not just optimizations at the software level. And then when it comes to the comparison to hardware, the benefit comes from using the cache-coherent interconnect, which avoids a lot of the overheads of data transfer from the CPU to the FPGA and the other way around. So that is one way of optimizing data center tax operations. And then I'll very briefly go over the second one, which keeps the hardware the same and instead applies software optimizations for the same purpose. So in this case, the type of data center tax that we want to optimize is memory allocation. And this is a project that was done in collaboration with Google, so all the numbers that I'm showing you here are from the entire production fleet of Google servers. So this is the same graph that I showed you before, and what we're focusing on is this red-ish region. So this is the overhead, the amount of CPU cycles that we spend for memory allocation. What Google uses as their memory allocator is tcmalloc, and it's not just Google, it's one of the most widely used production memory allocators in cloud providers. tcmalloc uses a tier design where there are different levels of caches for different types of objects. So there are per CPU smaller caches for small objects. Then there is the transfer cache and the central free list for spans, larger objects essentially. And then finally you have this backend cache or page heap, which is allocated at the granularity of huge pages. So we instrumented tcmalloc across the entire production fleet of Google, and we analyzed what are the key characteristics when it comes to memory allocation. And it boils down to three main things. First, there's a lot of variability when it comes to both the load, which is typical for cloud applications, and to the extent at which applications are collocated on the same machine. And that leads to very high cache miss rates for the front-end caches, these blue caches that are allocated per CPU. Second, there's a lot of heterogeneity in the platform. So whether this is because platforms have different configurations, so different amount of resources, or because the servers are of different generations. So some are older than others because you don't populate the entire data center on day one. And that leads to very varied data transfer overheads and cache pressure. Finally, there's a lot of variability when it comes to the lifetime of objects across different sizes. And the reason why that's a problem is because it makes it very challenging to reduce fragmentation on the backend caches, which operate on larger objects, spans, and huge pages. So if we look at this characterization in a slightly more detailed way, the aggregate CPU cycles that are consumed by memory allocation is around 6 to 7%. What I'm showing here is for the 6 largest Google applications, what that fraction looks like. And it's between 4 and in some cases up to 10%. If we were to compare this to more traditional CPU benchmarks like Spec CPU 6, which again is often used in computer architecture, it's a huge difference. So some of them don't even use memory allocation, and the ones that do use very little. Second, DC-Malloc experiences pretty significant fragmentation, both internal and external. And that can have a big impact on the amount of memory that is being used and the performance you get out of it. If we zoom in a little bit more into, out of all the CPU cycles that DC-Malloc is using, which layer in its hierarchy is using the most? So the most cycles are used by the front-end CPU caches. This is not surprising, because those are the ones that are used more frequently, and then less as we go towards the back-end. Fragmentation is the other way around. So the back-end, the largest caches, are most responsible for data fragmentation, and as we go towards the front-end, it's less. So given these characteristics, we implemented a series of optimization techniques inside DC-Malloc. It's deployed at Google. It's also in the open source community at this point. And they boil down to the following 3 techniques. First is implementing dynamic sizing of these per CPU caches instead of statically allocating everything, which might seem very simple in retrospect, but we needed all the instrumentation and data analysis to understand that that's where the problem was coming from. Second, we are leveraging the hardware topology to mitigate data transfer overheads between cores, which means that a core should mostly allocate from its local cache as opposed to remote cache partitions. And finally, we're looking at statistical data and using the statistical data on the lifetime of different objects when we're grouping objects in the huge pages, So that means that objects of a similar lifetime will go to the same huge page, and that reduces fragmentation a lot. So what does that mean in terms of performance improvement? So this is deployed across the production fleet at Google. We evaluated it across all applications and also the 50 largest ones. And I'm showing here the improvement in terms of throughput and the improvement in terms of how much memory is being used. And you might notice these are small numbers. However, you should keep in mind that this is already a very optimized system, and a 2% improvement in CPU cycles across 1 million servers is a huge improvement that you can use to accommodate a lot more useful computation. And same for the memory usage. So to wrap up, it's an exciting time to be working on cloud computing because there's a lot of changes happening, both on the hardware and software side. There's a lot more heterogeneity on the hardware. There's a lot more fine-grained, event-driven application frameworks on the software side. At the same time, we have to be very careful about how to minimize the data center tax overhead, which tends to become worse for microservices and serverless compute. There's 2 main approaches of doing that. One is through hardware acceleration, which keeps the computation the same but accelerates its execution. The other is through software optimizations. And I showed you one example of each. So with that, let me also show you the people that did the work. I'll stop here, and I'm happy to take any questions. Thank you.